Now we will continue making the signal processing part of our model. Here below we will make a control for our induction machine. We will start with SCADA input component. We will use this input as a reference for speed. Let's change label to speed RPM. With a double click in property window, we will keep signal type as real. The minimum value for the speed will be set to 200, and that is because we want to avoid the VF control at the very low frequencies, because machine cannot work with such low frequencies. The maximum value is 1700. The unit will be RPM, revolutions per minute, and the execution rate is TS. Now our reference will be expressed in RPMs in rotation speed. We want our PI controller to control electrical angular speed, so we have to convert our SCADA input speed RPM value. For that purpose, the gain component will be used. Gain value has to be set to 2 times NP.PI times PP divided by 60. This syntax is new because I used the predefined PI value from the NumPy library from Python. We will inherit the execution rate from SCADA input. We will close this block. The next thing that we will insert is a sum block. The first input will be plus, and we want the second one to be minus. Change the signs to plus and minus. We will connect the gain output with the plus input. The second input will be used for measured speed of our induction machine. In this case, we will use goTo and from components. I will zoom in the speed output and take the goTo component. Change the tag name to speed. We will do almost the same near the sum block, but now we will use the from block. Before we connect this signal to the sum block, we have to use a gain. Right now, this is a mechanical angular speed, and we want to convert it into electrical angular speed. We will multiply by a pair of poles, PP. Another thing that we can do here, because we want to observe the speed of the induction machine, is to use the probe and change its name to speed. Of course, this is angular speed, and we want to observe the rotational speed, so we'll use the gain component. In this case, we will type 60 divided by 2 times NP.PI. Now we got the rotational speed. Next, we will make a SCADA input component which will be used to enable or disable inverter through enable input and to enable or disable control. The same signal will be used. We will take the SCADA input component and change its name to enable. In property window, the minimum value we will set to 0 and the maximum value to 1. The execution rate will be defined as TS. Let's close this window. Now we will connect the SCADA input to the inverter input, and we will send the same value near the sum component with the goTo block. We will take the goto block from the library, name it enable. Near control, we will use a from block, and we will name it enable. If we double click again, we will see a matching tag. It means that we have connected them correctly. Now we will use a simple product block, which we will multiply the output from the sum block. If the enable SCADA input is 0, the output of the product block will be 0. And if the enable SCADA input is 1, the output of the product block will be the same as the signal from the sum component. In the first session, we have made the PI controller from a gain block and an integrator. Now we will use the pre-made PID controller from the Typhoon library browser. We will change the label to PI. Here in the component properties, we will change the controller type to PI. The proportional gain will be 0.9 and the eternal gain will be 4.9. In Advanced tab, we will enable limit. For the upper saturation limit, we will type value 550, and for the lower, minus 550, and we will enable anti-wind up. We can close this window now. Our icon has been changed. At the output of the PI controller will be the desired electrical angular speed. Now we will insert an integrator, which we will use to make a reference angle for the sine components, which will be used later. Let's take the integrator. We will double click on it and change a few things. First, we will change the external reset. We want it to be on raising edge. And we want to show state port at the output of our integrator. State port is the same value what we have on the integrator's output, but with unit delay. When we apply the changes, we will see that the reset input appeared and the state port appeared on the output side. We will connect the PI controller to the integrator, and at the output we want signal whose waveform will look like SAW signal. To make such a signal, comparator will be used. Let's take comparator from the library. We will double click on this block. So how does it work? If the non-inverting input is below the inverting input, the output will be 0, otherwise it will be 1. We will connect the comparator output to the reset input. Connect the state port to the non-inverting input on the comparator, and the value that we will use for comparison is a constant value. 5 constant components. Flip this block and we will connect it. For value, we will type 2 times np.pi. For the execution rate will be TS. We want to reset the output of our integrator after every rotation of the motor. Now we have a reference angle for the sine component whose output will be the input for the three-phase inverter. We will find trigonometric function component. It is a sine block. We will copy this one and paste it 2 times. Integrator's output has to be connected to the first sine input. The second and the third sine we have to make a phase shift. For this we will use the sum block. We will change the signs to plus. Applying changes. We will do the same for the third sine. Here we will add 240 and 120 degrees. On that way we will make a phase shift for the three-phase system. We can copy this constant, flip it, and connect it to the second plus input. We will change the value. Expressed in radians, it will be minus 2 times np dot pi divided by 3. We can copy this constant, connect it here, and change the value to minus 4 times np dot pi divided by 3. That will be minus 240 degrees. Now we will connect it to the reference input. At the output we will get sine signals. We want to make some kind of a modulator, and we will change the amplitude of sine signals, and in this case we will change the voltage of the three-phase inverter. We will use a product block. We will copy it and paste it to get 2 other blocks. We will connect the sine blocks with the product inputs. And now we will make a voltage control. We will use the signal from the PI controller multiplied with already calculated VF ratio. We will do this using the gain component. Rotate it and connect it to PI output. For the gain value, we will type our constant value from the presentation. It is 0.02 divided by 2 times np.pi. And apply the changes. If the voltage starts to raise above the value of 1, we want to stop this raising and keep it constant on number 1, so it cannot raise anymore. In this case we will use the limit component, and for upper limit we will type 1. For lower limit we will type 0. This means that if value is higher than 1, the output of limit component will be 1. Once we have finished this, we can bring limit component output signal to the product inputs. And we can finally got the reference value for the inverter. Do not drag 3 lines separately to the inverter. I will use a bus join component. Let's type join in search bar and drag and drop. I will change the number of inputs into 3, and it means that we will convert all 3 values into vector and every simulation step. We will receive the reference value from the from block. Let's take from component from the library and change its tag to reference. To unpack vector, we will use the bus split component from library browser. Of course, we must define the 3 outputs. We will connect the first output to the first leg of the inverter, the second one to the second leg, and the third one to the third leg. Now we are almost done with our model. We just have to insert the probes to observe certain signal within the model. For example, we can observe the voltage output. In that case, we need to convert voltage between 0 and 1 into the RMS value. In this case, we will use gain and we will type RMS value of the voltage 230 volts in the gain field. We will take the probe, connect it on the gain output and name it voltage. If we want to observe the integrator output, we will duplicate probe, paste it near the integrator, connect it to the integrator output and change its name into int out. We can get frequency from the signal. We will use the gain, rotate it, connect it to the PI controller output, and we will type 1 divided by 2 times np.pi. I will duplicate same probe and name it frequency. Now we can observe the voltage, the integrator output and the frequency during our simulation. What will be interesting for observation is the sign out. We will take one probe, change the name to sign out, everything is set up for signal processing part. Another thing we have to do is to use the SCADA input to define the load of our motor. Let's take the SCADA input, connect it to the load input, change its name to IMLoad. The minimum value of the load will be 0 and the maximum value will be 5. It is a 5 Newton meter load because our parameters for the machine model are for a small machine. The execution rate will be TS. Of course, we can change the unit to Newton meter. Apply the changes. We can even observe the output torque of the machine within SCADA panel, so we will take the probe. Change the name to torque. Now we have to explain something really important for our power electronic part. If we double click on the 3-phase diode rectifier, we will see that the rectifier consists of ideal switches. Their weight is 3. Even for the 3-phase inverter, the weight of these components is 3. So the overall weight of this power electronic part is 6. Now we will open the presentation. As we can see, in that case, if the overall weight of the power electronic converter is higher than 3, we have to use the core coupling component actually to split our circuit and to use 2 cores instead of 1. core coupling is the ideal transformer with a 1:1 ratio, and it inserts one simulation step delay. The core coupling component looks like this, and it consists of a red and a green line. The red line is the ideal current source of ideal transformer, and the green side is the ideal voltage source. More information about core coupling component can be found in Documentation Hub. Now we will use the core coupling component in our model. We will just type core coupling in the library browser, and in this case we will insert it to the DC side. We will use the single phase core coupling and drop it on the DC bus. We can set up snubbers for the current source side and for the voltage source side also. In this case, we will use the snubbers for the voltage source size, and it is one resistor with a value of 0.01 ohms. We will close the core coupling properties. Now we will save our model, compile and run simulation. Compile and run. Okay, we have an error in from component. It should be speed. And now we can compile and run our simulation. And it's working.